In this lesson, we'll cover polynomials, including their graphs and properties. To start with, the definition: a polynomial function of degree n is any function of this form. The a's that appear in this expression are constants or coefficients, and they're being multiplied by x's to powers. Here's like an x squared and x to the first, and this ... means it can be as large as possible. Like maybe it goes up to x to the power of 50 or 500 or something like that. Since we don't want to stop where the number can go, that's why we use this ... There's a trend, and that trend continues. The degree of a polynomial is this number here. It's the largest exponent that you encounter. And because of this, we need the leading coefficient, that's this term here, a sub n, we need that to be non-zero. One other thought about this definition: this thing is not factored at all. There are no parentheses that appear within this equation. And because of this, I'll just note that this is in expanded form, meaning this thing is completely multiplied out. And when that happens, it's very easy to determine the degree. It's just the largest exponent that you see. So maybe to start with here, I want to list out some examples of polynomials, indicate the degree and the leading coefficient, and then over here, list some things that are not polynomials. So maybe to start with here, I'll say f of x is equal to 10x to the 50th minus 4x cubed plus 1. So this thing is definitely a polynomial. Notice that there are missing terms, but that's okay. That just means the coefficients on those terms are 0. But here we start with a number 1, that's like the a sub 0. There's no x or x squared, that's okay. But then we get to an x cubed, so that's like moving down in this direction. And its coefficient is negative 4. And it stops when you get to x to the power of 50. So in this example, a sub n, the leading coefficient, is 10, and the degree is equal to 50. Maybe another example would be something like, how about g of x is equal to negative x cubed plus 2x squared minus x plus 1. So definitely of smaller degree. In fact, the degree here is equal to 3, and the leading coefficient is equal to negative 1. How about one more? I'll call it h of x. That could be something like, how about x to the 5,000th power minus 1, also a polynomial. So here we have that a sub n is equal to 1. It's not written in here, but there is a positive 1. And the degree is 5,000. Now what about things that are not polynomials? So that'd be something like, maybe f of x is equal to, you could have like 2x to the 4th, so far so good, minus x squared, not a problem. But maybe if you had like x to a fraction, like 3/2, okay, this thing is not a polynomial. And the reason for that is because of this exponent. All of the exponents within a polynomial must be positive integers, and 3/2 does not fall into that category, so no good. How about something like, all right, g of x is equal to, you could have negative 1/2 x to the 10th. That's not a problem. Here we have an integer exponent. This is a fraction, but the coefficients can be any numbers that we want. That's no problem. But then let's say I added on the square root of x. Okay, that's an issue. Up here there are no square roots. Here there is, so already that doesn't work with the definition of a polynomial. Let's look at one more. Maybe let's call it like y. Y is equal to, all right, something like, how about the absolute value of x plus 1 minus 1 over x plus x to the power of negative 2. So a lot goes wrong here. You can't have an absolute value, so like, that's no good. No absolute values. You can't have fractions. You can't have variables within the denominator. And here we have a negative exponent, so that's an issue. So with this one, no absolute values are allowed. Fractions where you have a variable in the denominator are not allowed, as well as negative exponents. So now that we've talked about what is and what is not a polynomial, let's talk about what the graphs of these functions look like. Before we look at example 1, I'd like to define something called end behavior. This is a term that's used to describe what is happening on the ends of your graph. It turns out that for a polynomial, the degree will tell you a lot about what the ends of the graph look like. So let's check this out in example 1, where I have a graph of f of x, which is 5x to the fourth minus x cubed minus 10x squared plus 3. If I look at this equation, if you want to know the degree and the leading coefficient, you only have to focus right here. This polynomial is an expanded form, therefore we can look to this term to indicate that, well, the degree is equal to 4. That's the largest exponent. And then the coefficient for this term, which I'll denote a sub, well, I'll call a sub 4, it's equal to 5. These two things will tell you what is happening on the ends of the graph. And when I mean the ends of the graph, I'm talking about this spot here and this spot here. So like this is the middle of the graph, and then here are the ends of the graph. And notice it's going up to positive infinity on both sides of the graph. It turns out that if the degree is even and your leading coefficient is positive, then the ends of the graph have to go up on both sides. The reason for this is if you actually just graphed 5x to the fourth, you get a U-shaped graph, much like the graph of x squared. So I'm just going to trace this in here. This is a graph of 5x to the fourth. Goes up and it goes up like this. So a lot like when you have an x squared, it goes up on both sides. The same thing is true for x to the fourth, x to the sixth, and so on. Now there's all these other terms, and they make the middle of the graph different. But when x becomes big, as you go in this direction and this direction, these terms become insignificant, and it's only this part of the function that determines what the graphs are. So even before I graphed this, I looked at this equation, I thought, oh, I look here, this number is even, this number is positive, and so when it comes to the end behavior, I'm expecting it to rise on both sides. I think the only other thing to point out with this example is, well, what if a sub 4 was negative? If this happened, if the degree was even, and this number was, let's say, like -2 or something like that, the only difference is the graph would be upside down. There would be a reflection over the x-axis. So in terms of the end behavior, instead of going up on both sides, rising on both sides, it's going to fall on both sides. So just looking here, I know a lot about the graph. I don't know anything about the middle of the graph, but I do know it has to go up on both sides. Let's apply the same logic here in example 2. Here's a polynomial. I included its graph, but I'd like to use the degree and leading coefficient to describe the end behavior. So this right here, since the polynomial is an expanded form, this is where I want to look if I want to know the degree. Well, the degree is equal to 7. That's the largest exponent. And a sub 7, the leading coefficient, is 2, which is a positive number. What is different here is the degree is not even, but it is odd. And if you have something that is odd degree, it won't go up on both sides, but it'll alternate. One side will go up and one side will go down. So here's the end behavior of the graph. So in this case, we can say on the left, it will fall, so it goes down, but then on the right, it will rise. And the reason for this is, if you actually just graph 2x to the 7th, if you only were to graph just this term, you get an equation that looks like this. It would come up like this, go through 0, and then cross over and continue to go up like this. Much like the graph of x cubed, x to the 5th, anything with an odd exponent will have to move up, go through the origin, and continue moving up. The only other thing I'd like to point out here is, well, what if it were that a sub 7 was negative? Again, it will just alternate. This side will go up, and this side will go down. So I'll say on the left, it will go up, it'll rise. So it goes up, but on the right, it'll go down, it'll fall. Let's look at a couple of other definitions with polynomials. First, a 0 is any x value that makes the function equal 0. So like if you look at this equation here, it has exactly 1, 0. That's the spot. At x is equal to -1, the function is equal to 0. Over here, this function also has 1, 0, and that's positive 2. You can actually see that by looking at the equations. -1 makes this factor 0. Positive 2 makes this factor 0. But there's another term, something called multiplicity. The multiplicity of a 0 is the value of the exponent for the corresponding factor. So that's going to be this number here and this number here. So the 0 of -1 corresponds to this factor because -1 makes the factor 0. And then this number 4 is what we call the multiplicity. So I just made a quick note of that. The 0 is at -1, the multiplicity is 4. Now over here, as we said, x is equal to 2 is a 0, and the multiplicity is going to be this number here, which is 3. 2 makes the factor 0, the factor has an exponent of 3. So why is it worth mentioning this new definition when it comes to polynomials? Well, 4 is an even number, so this has even multiplicity, and 3 is an odd number, so we say that this has odd multiplicity. And notice that at the zeros, again, this one was at -1, this one was at positive 2. Notice that something very different happens at this 0 versus this one. If you have even multiplicity, the graph bounces off and stays on the same side at the 0. In other words, it does not actually cross the x-axis. If you have odd multiplicity, the graph will go to the 0 and cross over the axis. So with even multiplicity, the graph stays on the same side of the axis at the 0. But with odd multiplicity, the graph crosses over the axis. Now that's a ton of definitions, but let's see if we can apply all of them to sketch a graph of this polynomial. Can we use degree, leading coefficients, the zeros, and the multiplicity to get a somewhat accurate sketch of what this graph looks like? For starters, let's look at the degree and leading coefficients. Notice this thing is not factored, it's expanded. Therefore, if you want to know the degree, we can look right to this term here, and I see the degree is 4. Also, the leading coefficient, which is a sub 4, it's not written in there, but it's 1. The number in front of the x to the 4th is really a 1, so that is my leading coefficient. Now, I don't know the zeros, nor their multiplicities, but that's because this thing isn't factored. If we can factor this polynomial, it'll be a lot easier to determine these things here. So how do we factor this thing? I'm going to start by, removing a greatest common factor of x squared from both terms. So this function, I'll write it off to the side, f of x. You can factor out an x squared, and what is left over is x squared minus 36. This can't be factored any further, but this is a difference of 2 squares. I can break this up into 2 linear factors. That is, f of x is equal to x squared, and we get an x and an x. You have to have a positive and a negative, and a 6 and a 6 make it work. X times x is x squared, 6 times -6 is -36, and your middle terms cancel. You have a -6x and a positive 6x. So this completely factors as this. Okay, written this way, I now know the zeros. The zeros are the x values that make these three factors equal 0. So if I start with, let's say this one here, this is just x to the power of 2. The number that you put in place of x to make this factor 0 is actually just x is equal to 0. Likewise, we have another factor here. The number that makes x plus 6 0 is -6. And the number that makes x minus 6 0 is +6. Because we know these values, those are points that we can actually graph on the x-axis. So by that I mean, if I'm trying to sketch this function, I have a 0 at 0, but I also have one at -1, 2, 3, 4, 5, 6, as well as one at +6, 1, 2, 3, 4, 5, 6. All right, now what are the multiplicities of these zeros? If I focus on this one, I see it's coming from this factor. It has an exponent of 2, so 2 is the multiplicity. So I'll put that here. This is the corresponding multiplicity. Now this 0 came from this factor, and the exponent isn't written in there, but it's a first power, so 1 is the corresponding multiplicity. And likewise, this 0 came from this factor, and again, there's no number written in there, but the exponent is 1, so its multiplicity is 1. Okay, what that tells us is, at this 0, it's an even multiplicity, so it has to stay on the same side of the x-axis. But then for these two zeros, because it's an odd multiplicity, it has to cross over the x-axis. Here's how I'm going to put this all together. I like to first plot the zeros. I then use the leading coefficient and the degree to figure out the end behavior. It has an even degree with a positive leading coefficient. That means the graph has to go up on both sides. So on this side, the graph goes up, and it must do the same thing on this side. It rises on both sides. The rest is just a matter of taking this part of the graph, connecting it to the other side by using the zeros and their corresponding multiplicities. Okay, so the graph comes down like this. It has to go to this 0. The multiplicity of that 0 is 1. It's odd, so it has to cross over the axis. So something like this. Now, it goes down some amount, but eventually it has to go back up to this spot here. So I know it goes down some amount, but it's got to start going back up. Now it's going to go to this 0, and it either crosses or stays on the same side. That's determined by the multiplicity. Here's the 0. Here's the multiplicity. Since it's even, it has to stay on the same side. So it bounces off like this. Okay, it's going to drop down some amount, but eventually it has to go back here. Now, I know it's got to cross for this to make sense, but fortunately, the multiplicity is odd, so I know this thing goes up to the 0, crosses over the axis, and it connects to the other part of the graph. So like this. So that's it. That's what these definitions can tell you about a polynomial, a basic understanding of what the graph must look like. So here's a much better graph of the function from the previous example. So I just went to Desmos, I graphed it, it gave me this nice perfect picture. But it does look like my sketch. Here, notice the y values go up to +400 and down to -400. I mean, I really had to zoom out to get a decent window for the graph, but it does rise on both sides. It crosses at -6, stays on the same side at 0, and then crosses at +6. Another thing to mention is, because we have this really nice graph, notice that this thing is symmetric over the y-axis. So on the left and the right, it's a mirror image over this vertical line. That will always happen if all of the exponents in your polynomial are even. If all of the exponents are even in your polynomial, we say the graph has even symmetry. And what that means is it's symmetric over the y-axis. If it turns out that all the exponents in your polynomial are odd, we say the graph has odd symmetry. And if there's a mix of even and odd exponents, then it turns out the graph will have no symmetry, that is neither even nor odd. In our last example, same idea. I'd like to sketch a decent graph of this function using these definitions. To start with, the way that this polynomial is written is actually factored and not expanded, which is nice because you can determine the zeros and the multiplicity relatively easily. So let's do that first. If you want the zeros, there are only two factors, this one and this one. -3 makes this factor 0, and +4 makes this factor 0. So there they are. X is equal to -3, as well as x is equal to +4. Like we can go ahead and say, on the axis, 1 to -3, the graph equals 0 there. And at 1, 2, 3, +4, the graph equals 0 here. Also, I know the multiplicities. I'll put a 1 in here to indicate that at -3, the multiplicity is 1, and at +4, the multiplicity is 2. So I got that by looking at the exponents. This tells me that the graph must cross here at -3, but it has to stay on the same side here at +4. Okay, so we need more information. We need to know, well, what's the degree, and then what's the leading coefficient? Now, it's not obvious what the degree is because this thing is not expanded out. Like, what's the highest powered x term? That only makes sense if all of this stuff is multiplied together. We don't actually have to multiply anything out. We can just reason out what that number would be. Here's what I mean. If you took x minus 4 and squared it, from this term right here, you would have an x squared. Here, this x plus 3 is to the first power. There's really nothing to expand, but you do get an x to the first. And this is just the number 2. It's not going to do anything for the x's. If you multiply an x squared by an x to the first, what you end up with is an x cubed. The degree of this thing is 3. You can actually figure it out in this case by adding the multiplicities together. I like to think of it as, oh, here's a squared, here's a first. If I combine those by multiplication, it's got to be a power of 3. Therefore, that's the largest exponent, and therefore the degree is 3. The last thing is, it's like, what's the leading coefficient on this thing? You know, what is a sub 3 equal to? Well, we don't have to multiply anything out. I know over here, the coefficient on the x squared is going to be a 1. Here on this x plus 3, well, it's already a 1. But now this 2 becomes important. If you multiply a 1x squared by a 1x to the first, you do get a 1x cubed, but this 2 will get multiplied to that term, so it'll actually put a 2 in front of the whole thing. So here I know that a sub 3 is 2. And what I really care about, though, is that it's positive. All right, let's go ahead and try to sketch this polynomial. The degree is odd. That means on one side it has to go down and the other side it has to go up. And because this number is positive, it'll go just like that. It's going to fall on this side and it's going to rise on this side. So it falls over here and rises over here. A lot like the graph of 2x cubed. That would come up and look like this. Okay, we can now connect this side of the graph to this side of the graph. This has to go up to the 0. That's this one. The multiplicity is odd, so it has to cross over the axis. It goes up some amount, I don't really know how much, but it has to drop back down and go to this 0 here. For that 0, it has even multiplicity. That means it stays on the same side. So not a perfect sketch, but this is about what the graph will look like.